So it's with great pleasure for me to introduce today's speaker, Amy Braverman, who is from NASA, but not NASA in New York City, but NASA from all the way from California. And I was the one who put her name down for this lecture because I took on myself to bring more statisticians to this the lectures of climate data science, because I believe that a lot of time we talk about how to convert climate science with data science, and then data science includes statistics. In particular, that we're at LEAP, we want to bring more observational data into climate modeling, and I cannot think of a better speaker than Amy. So it's with great pleasure for me to introduce her for this.
My second introduction.
The second introduction.
Yeah.
That's very funny. It is a delight to invite to have Amy Braverman here. So Amy got her PhD from the UCLA in statistics in 1999. But she's been working at JPL since 1997 because she said she was the world's worst graduate student and they wouldn't give her an office after 7 years. Yep. And it took her 9. But she's making up for lost time. So we've known each other because we were each involved earlier in our careers in doing spatial aggregation or data reduction for remote sensing data. Amy's stayed the course and I have not. But we have had, I can't think, we were trying to think as we were talking last night about all the different conversations we've had about exactly this question, you know, when you make a remote sensing measurement, how well characterized is that? So I look forward to this. Thank you very much.
Robert. And thank you all for having me. It's really, really a pleasure and an honor to be here. I've heard about LEAP for many years now and have always wanted to visit. And then COVID happened. So thanks for having me. I am going to talk about uncertainty quantification for remote sensing data. That's the title I usually give this talk. But what's new in this talk is that we're now doing it in a way that respects the spatial context of an individual image. I mean, some of you may know that when remote sensing data are processed, typically for speed and to be able to take advantage of parallelism by using multiple cores, the algorithms are often applied 1 pixel at a time. And when you do that, you're sort of sacrificing the information that you might get by leveraging information from nearby pixels about a current pixel of interest. So this is this talk is very recent. In fact, you're the first people to get it, except that I tried to dry run it on Tuesday for some people, and it was a predictable disaster. So if it's a little rough around the edges, I hope you understand. The work is joint with 2 colleagues from JPL, Nicholas Bond and Jonathan Hobbs, and 2 colleagues from elsewhere, Emily Kang from the University of Cincinnati, who's been my spatial statistics coach for many years. And a young man named Joachim Teixeira, who is currently getting his PhD with Sudipto Banerjee at UCLA. Right, so there's the obligatory outline. I'm going to talk about some sort of conceptual stuff at the beginning and then go into a specific example involving a recent mission called EMIT, which is on the International Space Station and providing remote sensing data used to study the distribution of mineral dust on the from the surface of the Earth into the atmosphere in the hope of improving climate models. And I just have the first results of this enterprise to show you. There's not a lot of it, but there's some of it. So I'll show you what that is. When I thought of coming here, I wanted to make this talk at least seem relevant to what you're doing. So I gave it a little bit of thought and thought about AI and ML and how that is used in climate science. And I know that at least as of a few years ago, much of the emphasis was on climate model output and comparing the output of one model to the output of another model, or comparing the output of a model under one set of assumptions to the same model under a different set of assumptions. But perhaps I'm outdated, and remote sensing data provides a vast source of information for confronting your model predictions with actual observational evidence, with a caveat that you'll all understand in a few minutes if you don't already understand it. So if you're going to do AI, if you're going to do machine learning to learn about the Earth system from remote sensing data, it would be a good idea to understand what went into the remote sensing data that you're looking at, because as I like to tell many of my stat friends, there is no thermometer in space. That's not how we measure things. It's all inference. It's all inferred from electromagnetic spectra acquired from space, from spaceborne instruments. I know just sort of the basics, which is that the two major roles of remote sensing data in the climate modeling enterprise include the use of the data to develop parameterizations for subgrid scale processes that you can't resolve directly. But then also, I ran around in this space for a little while back in the 2011 range when I was working more closely with Robert, which is, can you actually develop, I think, what they called metrics for how well a particular climate model or a model run under certain assumptions was performing by comparing it to data. And in fact, NASA stood up a whole big thing that was called OBS for MIPS, if any of you have heard of that, which was an attempt to take NASA data sets and put them in a form that was more easily comparable to the output of climate models. These are typically gridded data sets at relatively coarse resolution. And I don't honestly know myself how successful that was. It seemed to me that because every climate model has its own output resolution, or at least that used to be the case, that this made things pretty hard, because then the first step you always had to do was to get everything on the same spatial grid if you wanted to do these comparisons. My beef as a statistician with all of this is that there is no uniformly accepted standard for how you describe the uncertainties that are attached to these remote sensing data products that are put out. And that really does compromise their utility, because if mission A reports uncertainty using a particular scheme that they cooked up for themselves, and mission B does the same, then there's no way to immediately compare the two based on their uncertainties. I mean, uncertainty is, in a way, I will use a pretentious phrase, a lingua franca for translating back and forth and understanding what the strengths and weaknesses of different data sets are. So I've been hopping up and down about this for some time, and so far NASA is not listening to me by providing money, but we can hope. So I do want to say that this is a work in progress talk. Not all aspects are fully developed. In fact, I've spent 4 years on this problem so far, which is sort of the speed at which I do things. And now you can understand why I was a bad graduate student. And most of that time was spent on learning enough spatial statistics, thanks to Emily Kang, to be able to program up what I wanted to program up, which has to do with learning how to model a spatial field as a Gaussian process. And the rest of it was stuff that followed on heritage that we'd done in other areas. The one overarching requirement for this kind of a methodology, which we are, and I shouldn't say NASA hasn't come through with money, I am the lead for uncertainty quantification for the upcoming surface biology and geology mission, which some of you may or may not know about. That's the next big NASA mission. It'll be the second contribution to what's called the Earth System Observatory, which is the next suite of remote sensing, Earth observing remote sensing missions. And the data that I'm going to show here is actually the precursor mission. The emit data is precursor for the surface biology and geology visible shortwave infrared instrument that is going to be flying. There will also be a thermal instrument. And there are many fascinating statistical problems associated with that new mission. One of the big ones is these new data sets are at 30-ish, 60-ish meter resolution, global land surface for a long time, hopefully more than the 3 nominal years of the mission. That's a lot of data, right? The EOS, that's Earth Observing System, era missions were more like 1 kilometer resolution. So you can imagine what the increase in volume is about to be. So we have to be able to do what we're doing in a way that's computationally feasible. Robert said there might be some people in the room who don't know a lot about remote sensing. So I just put together a couple of quick slides. Probably you can imagine what's going on here. You've got the spacecraft, that's the observer flying along. In passive remote sensing, the sun is showering the Earth with photons. those photons travel through the atmosphere and change energy states essentially as they travel through. So they're impacted by the gases in the atmosphere and the composition of the atmosphere. They hit the surface where they are scattered in different ways depending on the scene. There's also emission all the way through, which means that things are blurting out additional photons that had been, let's say, stored in the Earth before they're burped back out. And then those photons go back out through the atmosphere. The whole thing happens again, and they're seen by the satellite. The satellite looks down and discretizes the spatial scene below it into pixels, right? Because it's a big camera. And it also discretizes the electromagnetic spectrum into bins. And essentially what it's doing is counting photons that fall into different bins that are acquired over different pixels. So in every ground pixel, you have a high dimensional vector of what started out as photon counts and then through the magic of data processing become something called radiances. There is the signature of the composition of the atmosphere and the surface in what is seen by the spacecraft because it's been impacted along the way, right? And the retrieval problem in remote sensing is about inferring what the state of either the atmosphere or the surface or some property of the Earth is from those noisy spectra because the instrument observes with noise. A typical polar orbiting satellite has a trajectory like this. And if it's passive remote sensing, it's only taking data on the daylight side of the Earth. So depending how wide that swath is, you'll have gaps between swaths on the same day because as the thing goes around this way, the Earth is turning this way underneath it. Okay, so at NASA and other space agencies, I think most space agencies have taken on this terminology for how the data are processed. Level 0 are the raw photon counts. That's what gets dumped to the ground. And on the ground, there's this series of steps that take place. The first is georectification and calibration of the radiances. Georectification is assigning a specific location. I think you can think of that as a latitude and longitude to every pixel. And the calibration of the radiances kind of ensures that if the detectors have, decayed over time, that you put everything back so that the radiance in one spectral band is sort of directly comparable to the radiance in a different spectral band. Then the magic happens. That's called level 2. Level 2 is where we do this big inference procedure where we say, we've seen a spectrum. Now, what can we infer about the Earth from it? And that is done through inverse modeling. So my big take-home message is these data aren't data the way a statistician thinks of them. They are themselves inferred. And then there are 2 other levels of data processing that I won't go into here. Level 3 are the so-called statistical summaries of level 2 on a uniform space-time grid. This is how Robert and I met. This was something NASA mandated because in the EOS era in particular, there was so much data that your average scientist couldn't use it and maybe didn't care about 1 kilometer resolution. They were doing global studies. They wanted things maybe on a 1 degree by 1 degree grid. So the question was, how do you sort of summarize these data in a way that remains faithful to them, but makes them lower spatial resolution? So Robert and I both, I guess, cut our teeth on writing documents about how to compute means and standard deviations, which is how that has been typically done. So since these data are really inferred, yes?
So is level 1 is where all of the geodesic adjustments are made, where you take those curvatures and flatten them into the...
Yeah, that's right. That's right.
And to get it, I guess raster tile happens later.
Yeah.
But, okay.
Yeah. Yeah. I mean, it depends what the final format of the data being produced are. Most things are in HDF now, if that's familiar terminology. No, talk to you about that later. Since these things are inferred, we really should have uncertainties attached to each one of these things that we produce. So here's my model of an observing system. Think of this as what takes place in a single pixel. The things in gray are things that we do not get to know. The things in blue are things that we get to know. The true state of the system, whether it's the atmosphere or the surface or some combination, is I'm denoting that by X. Everything here is actually a vector, even though so I'm not going to make a big fuss about that, but nature is what we call the forward function. The forward function is what converts that state into a radiance vector. We think about that. That noiseless radiance vector is observed by our instrument with some measurement error epsilon, and it is that thing I'm calling an observation, is this noisy radiance, which is then put into this gigantic retrieval algorithm, which is a very complicated mission-specific piece of software that attempts to get back at that state estimate. Now, the retrieval algorithm itself, like I said, it's a big lump of code, and it has buried inside it a forward model, not to be confused with the forward function. The forward model is our best representation of what that forward function is, but it is not the truth. For speed and because sometimes we just don't know certain things, that is by definition, it has to be kind of a crude representation. B, what I've called B here are other parameters that typically the forward model, but also the retrieval need in order to execute. So spectroscopy would be such a thing. Those are things that you need to know in order to do the retrieval and in order to run the forward model. If the retrieval algorithm is an implementation of Bayes, which is common now, that B would include the prior mean and prior covariance matrix of the data that you're going to start with. And then I've recently invented something called gamma, which is computational artifacts. Algorithms, iterative algorithms sometimes don't converge to global minima. They only converge to local minima. Sometimes they fail. This is going to depend on things like the fineness of the solution grid, even the way you parameterize the vertical distribution of the atmosphere. These are all things that can cause uncertainty. So like I said, that R is often an implementation of Bayes that looks to approximate the posterior distribution of the true state given the radiance, which sounds like a perfectly reasonable thing to do, and it is. However, if you do that, the only source of uncertainty that is being incorporated there is the uncertainty associated with epsilon. And there are all these other choices inside the retrieval algorithm that are going to cause uncertainties. Like the gamma might really literally cause variability in what you get from one run to another run. Or if you just change the parameter slightly, change the B slightly, you're going to get a different answer because it might be chaotic in there. Who knows? So
may I ask you a quick question?
Sure.
Which instruments are you using?
I haven't gotten that far yet.
There are 2 atmospheric windows.
Sorry, I missed that.
There are 2 atmospheric windows.
Can you wait just a little bit?
Micron level? Okay,
Can
I'll
you
ask you later on.
ask me later on? Because I'm going to get to that. Okay, so I have come to the conclusion that if the definition of uncertainty that is useful here is the joint distribution between the true state and its estimate. And if I could know the true state, I could get at that. And the way I would want to express that uncertainty would be through the conditional distribution of the true state after seeing the estimate. Because the estimate now incorporates all those other assumptions and scientific knowledge that I was able to bring to bear in the retrieval procedure, as opposed to just relying on the radiance itself and propagating only epsilon. So now we are going to propagate uncertainty due to the B's and the gammas, as well as the epsilon. And much of that might reflect itself in terms of a bias here, because typically when the retrieval algorithms are run, people pick values, right? You pick a fixed value you use a spectroscopy that is fixed. You're not treating that as a random variable. The gamma might have a random component, but typically more often than not, the choice of a specific B to run this thing will be different. You'll get a different answer than if you choose a different B to run it. Okay, so what I'm after now is this conditional distribution of the true state after I've seen the retrieval estimate. How am I going to get at that? Because I don't know the true state. Well, I'm going to run a big simulation experiment where I'm going to get an ensemble of, let's call them plausible true states. And then I'm going to run this experiment here where I'm going to use for my forward function, and I know this is This is what we call an inverse crime, and I'll say more about that in a minute. I'm going to use my forward model to produce the synthetic radiances that that are associated with with each true state. I'm going to add synthetic measurement error. I'm going to get a synthetic observation, and then I'm going to push that through my retrieval. And now I've got, for every true state I put in, I've got a state estimate that came out. And that's an empirical ensemble that I can interrogate. Now, why do I want to interrogate it? I want to interrogate it because I'm going to put a probability model on those two things. And I need to estimate the parameters of that probability model. And then when it comes time to evaluating the probability of x given x hat, I will plug in a true instance of x hat, the state estimate. This is, without knowing it at the time, this turns out to be an instance of something that's very popular in statistics now called simulation-based inference, where you use physical modeling to generate training sets to train stuff, and it might be a neural network. In my case, it's going to be a Gaussian mixture model to learn properties of the system, and then you use that to make inferences, or you use that to express the uncertainty of the output when you have a real instance of the thing. Okay. So there is, I said that there's an inverse crime here. A friend of mine calls it that, which is in the way I set this thing up, I have used the same f hat both as the forward function and in the retrieval, and that is, everybody will agree that's overly optimistic. I mean, I think that's a useful thing to do for making sure your code works, but that would be way overly optimistic, because you'd be assuming, I'm not going to get to the end of this, because you would be assuming that your retrieval algorithm knows what nature's doing perfectly. So our solution to that was to say, well, can we corrupt our observation Y sim in a way that appropriately penalizes us for that? And we call that model discrepancy. So what we want to do, and this is a different talk, so you have to invite me to come back to give a talk about how we got at model discrepancy for our application. You're just going to have to trust me for this talk that we got it in, at least in the ballpark. And model discrepancy here is the evaluation of the true state by the true forward function minus the evaluation of the true state at my forward model, using my forward model. And that is sort of the corruption to Y that I want to add in order to do this penalty. And it's hard because I don't know what the true state is, so how am I going to evaluate this? And that's the model discrepancy talk. All right, let me go here. Okay, so now the other thing is that in the remote sensing world and in the climate world, spatial relationships matter, right? These algorithms are typically applied one pixel at a time, but when people go to analyze it, or when you go to compare it to your climate model, you're looking at a whole spatial field of these things. And so maintaining spatial context and making sure that we do this in a way that also provides not just the uncertainty within an individual pixel by itself, but lets us get at the joint distribution between what's going on in one pixel and another pixel, that's important. So instead of just doing the probability, getting some grip on the probability distribution of the true state given the retrieved state in pixel A, and then separately in pixel B, I want to be able to do things like give me the probability, the conditional probability of what's going on in pixel A, comma pixel B, given the retrieved estimate in pixel A and pixel B. I'll get to that in a little bit. So I need some spatial notation here. I need to distinguish between spatial locations. In spatial stat, we usually call the spatial location S, which is a vector of, say, latitude and longitude, or some kind of spatial index. So our true state vector at location S is x of S, and everything else as you see here. The one other thing worth mentioning here is that the retrieval algorithm is trying to be the inverse of f hat, but it's not, right? Due to all kinds of computational considerations and lack of knowledge. We wish it was, but it isn't. Okay, now if I have a spatial field, an entire scene of these state vectors, that's the blackboard X, and everything else as is. The modeled observation vector is what I get when I stuff x hat back into f hat. That's the y hat. The spatial field of measurement error is Those are typically taken as independent, identically distributed from pixel to pixel. So that's a giant diagonal matrix. And the model discrepancy matrix is big D there, which lives, by the way, in the space of radiances, because I'm going to add it to the radiance to corrupt the radiance to penalize myself for having committed the inverse crime. Okay, so here's a picture of the kind of simulation experiment I want to do. It's the analog of what I did above, where I wasn't concerned about spatial location. It starts over on the left there with the thing I'm calling XP for parent. Now, the parent that I'm going to use in what I'm about to do is an actual retrieved spatial field from the instrument I'm looking at, which is emit, which I will tell you about shortly. And I put this over here to remind you that that actually did come by applying our retrieval algorithm, and this little this less than sign here is my way of saying applied pixel by pixel. The retrieval algorithm applied to the actual noisy radiance field that we got, that gives me my my estimated state field x hat here, and I'm going to do something very bootstrappy here. I'm going to do what amounts to a parametric bootstrap. I'm going to take that one spatial field that I have, I'm going to fit a Gaussian process to it, and then I'm going to simulate multiple realizations of that spatial field. That's what's going on across the top. And if I do this right, then that stack of X stars there should have the same overall statistical structure as the original, which is X hat, but should show an appropriate amount of variability. And I know that in the world of observing system simulation experiments, people often just add white noise to try to corrupt their thing, but that is going to miss providing the proper spatial correlation that is natural to the scene that you would also want to mimic. So I won't go into that. So now we go from that, we stuff that back into our F hat. This is the first part of the inverse crime. I add the synthetic measurement. I'm going to undo the inverse crime by adding this extra piece of random variability in the spatial field of model discrepancy. And I'm going to get a stack of simulated radiance fields called the Y daggers there. And I'm going to put those in the retrieval, and I'm going to get these X hat daggers over here that are kind of, this is like that ensemble that we had earlier that matched the synthetic truth with its synthetic state estimate, but it's at the level of the entire spatial field at one time. Okay, does that make sense? Okay, good. All right.
So just to make sure your empirical noise, which matches the empirical noise in the thing you're observing,
Yeah,
occurs when you simulate from data or
yeah. The simulation from the GP is an attempt to mimic natural variability of the scene.
as opposed to using the naive way.
The naive way would be to say the scene is the scene, and I'm just going to add IID noise.
Which is done a lot. but
Which is done a
you
lot.
really cut it,
Right, right. And the other thing is that having that stack of things that I can see, but what's key to the uncertainty quantification aspect of this in the first place, it's also key to getting that model discrepancy.
Have you ever tried interrogating GP theta hat with regard to different versions of colored noise from signal processing to see if you're getting a mixture of colors? That
No.
might be helpful.
I've not tried that.
We'll talk about
We'll talk about that. Yeah, thank you. Typically that instrument measurement error is a pretty small component of the overall uncertainty that infects this. Or it might be, who knows? I mean, the largest bit of uncertainty comes from all the assumptions made here, including the forward model, and those computational compromises there. That's where you get a lot of uncertainty from. Oh, yes.
Could you just maybe give it like an example of what kind of parameters are in theta? What kind of parameters are in theta? Like just an example.
For our GP, we're gonna use a Matern 1/2. And the parameters of that would be a length scale parameter, which is sort of the correlation distance, and the overall variance of each, not of the noise, but we're now talking about modeling the natural variability of the scene. Does that make sense? All right. So if you look at this picture, I'm going to break this picture into two parts: the simulation part, which is where I spent the last 4 years and 9 months. And then there's the experiment part, which is the last 3 months. So I have a gross amount of detail on the simulation experiment that most of you are probably not that interested in, so I might just sort of flash by that. And if you want to follow up with me later about that, I'd be happy to do it. The experiment part is pretty straightforward also because we just used operational software to do the experiment, which was to push every pixel in each of these B sheets of X star through this system. Okay, so now our ensemble of spatial fields. Yes.
The Gaussian process, is it trained on multiple fields?
No, well, that's a question. In the initial instance that I'm working on now, the idea is to train it only on the particular granule of data for which I want to get the uncertainties. I'll say about that when I get to the application, because in order to keep up with the data flow, we want to be able to do this using data only from that scene so that I don't have to, you could, right? And there are some reasons why you might want to. If I trained the GP just on the scene I'm looking at, then the GP model that I get applies only to that scene. So what happens when I go to another scene? Am I going to get some kind of discontinuity, for example, at the boundary of the two scenes? That's a worry. So for that reason, it might be worth doing it on a whole day or a whole season or a whole year. And that's a decision that is yet to be made.
But it's mostly for the spatial variability and not any sort of temporal variability.
And not what, sorry?
Any sort of temporal variability.
That's correct. That's right. We're freezing this thing in time for the time being. That's right. Okay, so yeah.
Just a reminder,
Mhm.
there's people in Radio Land, so if people ask questions, can you summarize or?
Oh, yes. Okay. So that question was, what do you train the GP on? The single scene that we're looking at the moment, or on a whole day's worth of scenes or a month's worth of scenes? How do we do that? We haven't decided yet. We're too early on in the process. But if you ask me in a year, I might have an answer for you. Okay, so now, how are we going to summarize this? This is something I already said. I can certainly do for a given pixel, I can get the conditional distribution. If I do this simulation and I have capital B simulated spatial fields in my simulation experiment, then I would have, in any pixel, I have capital B instances of the synthetic true field and the synthetic estimate that goes with it. And if B is large enough, I can fit some kind of probability model, like a Gaussian mixture is what we have done when we did the non-spatial version of this, was to fit a Gaussian mixture model to that and produce the conditional distribution of the true state given the retrieved state in any pixel. But I already said that that's not enough for me. I want a user to be able to come in and draw a polygon around a collection of pixels and then somehow represent to them what the conditional distribution of all those true states are, given all their estimates. And I'll be perfectly honest and say I haven't figured that out yet. I think that's a very, very hard problem. And we're just starting to work on that now. So I don't have anything to show you of that nature. But what I do have is that single pixel version that I can show you for a couple pixels here. The other part about this is, how can we make this fast? It's got to keep up with data flow. The first 2 years of trying to do this, I spent trying to estimate the parameters of my spatial field using gradient descent. And that took way too long, partly because the field was way too big. And I should also say, I need a non-stationary model here, not a stationary model. So I will show you, now I will show you about, the emit mission. Okay, so the answer to the question which was asked, which was, what instrument are you using? It's emit. The Earth surface mineral dust investigation experiment, you can see it's on the space station. So it's not doing the polar orbit, it's with the space station, which means it's kind of got an odd orbit. But for the purposes of this talk, that's not super important. It measures in the visible shortwave infrared. It has 285 channels. So those radiance vectors are 285 in length. So every pixel, every 60-meter pixel on the ground has a 285 dimensional radiance vector associated with it. You can see the science goals here are noble, of course. And that's kind of a picture of what an emit radiance cube looks like. It is 1242 pixels in one dimension, 1280 pixels in the other horizontal dimension, and there are 285 radiances in each one. Now, you may ask, what is the state vector we're trying to observe? Well, it's something called surface reflectance, which has the same dimension as the radiances. It's also a 285 dimensional vector. And what it effectively is the contribution to the total radiance that you can ascribe to the surface. So this process of converting a radiance to a reflectance in the field is sometimes called atmospheric correction, which is where we attempt to take out the influence of the atmosphere. Because the atmosphere here is a nuisance. It's the surface we care about. There are many other places where the atmosphere is what we care about and the surface is the nuisance. But in this particular case, it's like this. Folks have Clive Rogers' book in the year 2000. Many of you are probably familiar with that. He put forth a method for applying Bayes' rule to this problem to try to infer the posterior distribution of the state given the radiance from the radiance measurements, the noisy radiance measurements. Here, the atmospheric correction is done along the way. You take this full state vector, which is 287 dimensions, not 285, which includes characterization of the water vapor content and aerosol characteristics of the atmosphere. You do the Bayes thing, and then you throw away the water vapor in the atmosphere, and you're left with the atmospherically corrected surface reflectance vector that is then going to be further input into algorithms to derive things like this mineral composition of the surface. It can also be used for studying snow and ice properties on the surface and vegetation characteristics, which is what SBG will do. That was not part of EMIT's primary mission. Here's just a short thing on the OE retrieval. It's an iterative algorithm that searches for the map estimate. Remember, we're doing this one pixel at a time. So you're dealing with a sample of size 1 here that you're trying to do this on, which to a statistician seems a little hinky, but that's what you do. Sort of notably here, what it gives you under the Gaussian assumption, the map estimate is the mean of the posterior, and the covariance matrix associated, the 285 by 285 covariance matrix of the posterior is jigged up this way as a linear approximation, which Noel Cressy, some of you know who Noel is, pointed out at one point. That's actually not right because the posterior covariance should not depend on the state. And what you see almost universally when you do this is that these covariance estimates are too small, way too small. And sure they are, because they only propagate the instrument measurement error. Now, some people have tried to do other things to augment that, but that's still not standard practice. Okay, so it's important to emphasize here that our objective is not here to improve the retrieval or the forward model, although what we're doing here could be used to do that. It is to quantify the uncertainty in the operationally retrieved quantities, warts and all, artifacts and all, bad guesses and all, as estimates of their true counterparts. So we carry out that spatial simulation experiment to understand how the different assumptions along the way in this chain affect the flow of information from start to finish. Let's see what I want to do. So there's an emit scene. That's everybody's favorite emit RGB image over Mono Lake, California. You can see it's a lot of snow, a lot of mountains, some water. And it's wintertime, so there might not be much vegetation that can be seen there. It's that 1280 by 1242 image. I truncated 1242 to 1232 for reasons that are coming, having to do with the number 16. I think I need to talk about two different ways of arranging the data. Different ways of arranging the data might be useful in different settings. One is what I call the array form, which is the cube, right? 1232 by 1280 by 285. The other way is what I call the tabular form, where we let each row be a pixel, and each column be a wavelength. So that would be, in this case, it's about 1.5 million rows and 285 columns. And when we're talking about the array form, I got into Julia a couple years ago. And Julia has a wonderful thing called a block array, if anybody knows that. So you can index a pixel the normal way, which is to say pixel I, pixel j, row and column. But you can also say, I'm gonna subdivide my big array into blocks of a certain size. And then you can index any pixel within any block as the j-ith pixel in the l-kth block. And that turns out to be convenient too. So I just want to say we did that. Now here's the meat of the simulation part of the experiment, which is to take that parent field, fit the GP to it, and then simulate from the GP. And as you can imagine, and do this in a non-stationary way, by the way. So how are we going to do that? I'll get to the non-stationary part in a minute. First thing we do is project we take XP in its table form, do a principal component projection of the data into the leading principal components. 6 principal components here capture virtually 100% of the variation in the data. So that was kind of happy. And those columns of the projected data into those 6 dimensions are W1 through W6 here. And we're going to hold W1 and W2 constant and call that the trend in our simulation. And then we're going to fit separate Gaussian process models to W3, 4, 5, and 6 and simulate from those, superimpose them back on the trend, undo the principal component simulation, and then we have our simulated field. Okay, and by the way, yes.
So the Gaussian process here does the spectral covariability as well as the spatial covariability.
Yes.
Right. Okay.
Yes. The question was, does the Gaussian process account for spectral variability as well as spatial variability? And I think the answer to that is kind of yes. The principal component transformation is the way of getting that in there. In order to do this in a non-stationary way and for computational speed, we're going to divide the scene into a 77 by 80 array of blocks. And we're going to fit those 4 Gaussian processes separately in each block using a stationary Matern model. And then when we come to actually simulating the replicates, I have not a very clever trick for how to do that in a way that leads to a non-stationary field. I think I already talked about this. Reverse the principal component projections. There we go. I'm sure many of you have done this kind of thing yourselves to reduce dimension. This is just some details on the principal component transformation, which is to make clear the top row here, which is that the covariance matrix of the table form of X is what we're using. Here are the principal components, the 6 principal component fields, and there's the scree plot over there. And we chose 2 to fix to be the trend because we started with 1 and it ended up not working properly because there was too much natural variability in the scene if we simulated over 5 of the 6 principal components. So there's that. And that's kind of the blocking strategy there. This is not a 77 by 80 blocking. This is like a 10 by 10 blocking, but you wouldn't be able to see anything. It would just be a big red blob if I did the 77. So we sequentially number the blocks in this way. And then for each block, we fit a Matern 1/2 with those length scale parameters. And now the problem becomes, how do you estimate those the length scale and the variance parameters of the Matern, that's the sigma LK and the rho LK, in a way that's fast enough for this problem. And that's why I said, 2 years was trying to make gradient descent do that in under 10 minutes a block, and that was too much. So then I went to the joint statistical meetings last summer, and I went to a session on something called amortized inference, right? And there were some folks there, Matt Sainsbury Dale and Andrew Magnon, among others, who talked about this Julia package that Matt has created as part of his PhD work at the University of Wollongong, called neural estimators. So I kind of like this. I hope I'm not blowing it out of proportion, but it's a brilliant idea. And what it says is, fitting a spatial model can be computationally expensive. But so what if you did the following? What if you took a bunch of plausible parameter values on some kind of parameter grid, and at each grid point of the parameter grid, you generated a spatial field or a pile of spatial fields at that parameter value, and then you used a neural network to train that thing backwards, which is the input then becomes the spatial field and the output becomes the parameter. That's what they did. It was very clever. It's very, 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 very fast. It's almost instantaneous for the prediction part. Training it for that emit granule took about 30 seconds, which seems fairly reasonable. So that is what we used to get the spatial parameters for each of the blocks. And there they are for blocks 3, 4, and 5. I couldn't get block 6 on, or W6 on there without making everything too small. And it's, looks okay. I haven't done anything to check it. I admit that. Matt is actually working on that. He's collaborating with us now, and we are actually working on that. But then the question is, how do you do the simulation? And many of you might be familiar with the notion of conditional simulation of a spatial process, where, okay, so now I have my blocks. I'll go to the first block. I'm going to go to the first block up here, number 1 in the upper left corner, and I'm going to unconditionally simulate that from the Gaussian process for that block. Then I'm going to go to block 2, and I'm going to simulate block 2 conditional on block 1. And then I'm going to simulate block 3 conditional on block 2, and so forth and so forth. Except that is too expensive, because those are very high. Those are 256 dimensional simulations, because 16 by 16 is 256. So we did instead is, when we got to block 2, we conditioned only on the bottom edge of number 1. When we get to block 3, we condition only on the bottom edge of number 2. When we get around to the top of the next column, we condition on the left edge of the previously simulated block, which would be number 1. And then we get to this one here, we condition on the bottom edge. The bottom edge, in other words, you condition only on the edges of the adjacent blocks that have already been simulated. So I will go past that. Okay, so that's what's being shown here. There's all kinds of detail in the backup slides. I'm not going to go into it for time. This, believe it or not, if you can see it, I hope you can see it. Maybe you can't, not on this screen. This is actually an animation. Yes.
When you do the edge conditioning,
Yeah.
be very careful with regard to how boundary conditions they act as artifacts.
Well, you get what you get, right? I mean, it is what it is.
Yeah.
In that simulation. But because of the screening effect, it should be true that the conditional distribution of a block, given a set of conditioning variables that just happens to be the edge of the adjacent previously simulated block, should only depend on that, right? Okay. You probably can't see it. I think you can't see it in the room at all, but the W3, 4, 5, and 6 are changing slightly here. W1 and W2 are not, because they're treated as trend. So this is sort of the scale of the natural variability that is being simulated here. And it is, it has the statistical properties of the original parent data set, because that's how we created it. So here's an RGB image of the same thing, and you can see it maybe a little bit better here. So if you just put IID noise on there, you'd still see the overall spatial structure with the mountains and the lake and all that, but the fuzziness would just be white noise. So here we have kind of spatially structured fuzziness. Okay, so now the experiment part. I think I said what I wanted to say about that, which is that we just push this thing through the operational software after deriving the model discrepancy. The model discrepancy is not part of the operational software. I had a little bit of detail on how those things are. I think I already said the measurement errors. There is actually a separate measurement error for each pixel that is calculated from a formula that was fitted at a time when they had the instrument in the laboratory, and it corrects for certain things. I don't really know all the details of that. The derivation of model discrepancy is a completely separate talk, and I would love to talk to any of you about it, because I imagine that model discrepancy, characterizing forward model error, forward model structural error as separate from the input errors, would be something that is potentially of interest to a lot of people in a lot of areas. So armed now with the result of the simulation experiment, going to a single pixel at a time, we learn the parameters of the Gaussian mixture model using that synthetic joint distribution. We used the R package mclust to do that, which conveniently you can call directly from Julia. This is just a little bit on the Gaussian mixture density. Gaussian mixture is a family of Gaussians, each of which can have its own mean vector and covariance matrix and a set of mixing weights or probabilities. And so this model has those parameters. Those things are all learned from the simulation. Yada, yada, yada. I will not dwell. Then we have the usual formulas for Gaussian conditioning. So if I want the conditional distribution of true state given retrieved state, I plug them into this equation. And the daggers and the stars refer to different things that are learned from aspects of the simulation. The key thing here is that if I wanted the conditional distribution of x given x hat dagger, if I wanted the conditional mean, I would use this formula. If I wanted the conditional variance, I'd use the one underneath. And if I wanted the mixing weights, I'd use that one. And what I have done here was plugged in x hats and x's from the simulation just to illustrate. But in reality, I don't know what the true x is. That's why I'm doing this. And what I'm going to plug in is an actual x hat, not a simulated one from the experiment. Does that make sense? Or seem clear at least? Okay, finally, I can simulate from that distribution if I want to visualize it. I can simulate from that conditional distribution. So as a way of looking at the result of that after having pushed everything back into the original space, the original reflectance space, I'm not gonna dwell on that. That's the kind of thing we got. So what you're seeing here is the blue envelope are draws from that conditional distribution of the true state given the retrieved state. The green line is the actual retrieved state. And I thought I try telling remote sensing people that their retrieval has a problem, they won't like it, right? Nobody likes being told that. They don't, especially if they've already produced a gob of data that way. But I showed this to somebody on the emit team and he didn't scream. He thought these results were plausible. What you see here is that there is some bias. In the blue envelope this represents 100 draws. And remember, I only did the simulation. I don't think I said, I only did it with 10 replicates because it was hard. And each replicate is 2 gigabytes. So it was a little difficult to maneuver around. We're going to beat that by putting all the computations on a supercomputer instead of doing them partly on my laptop and partly on the laptop of Nicholas Bond. But I showed this to him and his was, yeah, I mean, it could be. This feature here, this sort of persistent feature here, between 500 and about 750 nanometers in all the plots is indicative of misspecified atmospheric properties, particularly aerosol properties, and potentially also the failure to include 3D effects of radiative transfer due to mountains and topography. And that you can well understand. I mean, people are well aware that the routine radiative transfer algorithms that are used are typically 1D algorithms. So they're not picking up some of these effects of topography, and that you would expect cause some kind of issue. Also, the spike over here at about just short of 1500, Nicholas said, ignore that. That's at the shoulder. I'm not sure what that means, but some of you do. That's at the shoulder, and that's kind of a known artifact. So I was pleasantly surprised to get something that I wasn't yelled at and screamed at about, and that my collaborator thought was at least plausible. And I'm not saying this is the final answer. There are lots of decisions that were made along the way that could affect what this ends up looking like, and there's an awful lot of tinkering to be done before we get there. Yes?
Actually, you said it didn't quite catch.
This is some kind of impact, this spike here, that has to do with the fact that there's a gap. And he didn't elaborate. We didn't have time to discuss it in great detail, but he didn't seem concerned about that. So I'm gonna try to wrap it up quick here. So all this, we call this thing an observing system uncertainty experiment instead of an observing system simulation experiment. And all it is an observing system simulation experiment that people in the field do all the time, but with maybe a more careful treatment of how you create what I think you would call in the Aussie world a nature run. What you do with that, you use an ensemble there instead of a single thing, and maybe people do that in Aussies too, I don't know, and a more careful treatment of how you interrogate the output. I've seen lots of people just looking at root mean squared error as a measure of how these things relate to each other, but that's really trying to clobber a lot of information into a single number. It blurs between bias and variability, and I think people do care about that. This is an instance of this notion of simulation-based inference, which a fella at Kyle Cranmer at Wisconsin, who's now the head of the Data Science Institute there, came up with. He's a physicist, but very clever and very sort of feels kind of modern, and has connections to likelihood-free inference in statistics and things like Bayesian computation. Let's see, what else do lots of methodology questions here for my stat friends, and for my domain scientist friends, like where do you draw the line between what's considered trend and what you're going to simulate over? The first time I did this, when we just used the first principal component as trend, what we ended up with was a whole bunch of negative surface reflectances and negative radiances, and that is just not physical. So that's when we went to number 2, but there would be many ways. Nothing says you have to use the first of anything. Maybe I should freeze one of the others. But who knows? Okay, so what we're trying to do here is we are trying to mimic natural variability. We're trying to find a way to mimic natural variability. This is not necessarily the Rolls-Royce method of doing it, but it is a method of doing it. And that leads to the question of what exactly do we mean by natural variability? You know, what is it when you only get one look at the scene on a particular day at a particular time? What does it mean to be considering variability in that context? There is only one on that day at that time, but nonetheless, I mean, in statistics, we face that all the time. We're talking about alternative plausible outcomes, as far as I can tell. I mean, that's my take. The statistical properties of these neural estimators, that is a big deal. There's a lot of people working on that right now. There's Matt Sainsbury-Dale tells me there are people out there working on convergence results for that. So that's a relatively new thing. Like he said, always check it against MC, which I haven't done. I'm hoping he'll do that for me. We need emulators for both the forward model and the retrieval. It takes too long to run these things. The only reason we could do this for this exercise was because we used 128 cores and so on. But in order to keep up with operational processing, it's going to have to be a lot faster than that. The question of over what data should the model be estimated, the Gaussian mixture, that's a good question. That is exactly one of these methodology questions. And is there a way to do this kind of description of the conditional distribution of the true state given the retrieved state for multiple pixels at the same time that is feasible? And when you don't know, I mean, a user, who knows whether Robert Pincus is going to go in there and draw a little tiny box around a few pixels or a big box around a lot of them. So we're going to have to face that. Whoops. And here's what my stealth reason for coming here is that this whole idea originated from some work that I did about 10 years ago in trying to develop better ways of assessing whether 2 climate model runs were quote unquote similar enough or similar to within their internal variability. And this GP simulation idea follows naturally. We did that work for time series, where we broke down a time series. We did a wavelet decomposition of time series, and we simulated over the finer scales. And then my colleague Ansu Chatterjee, he developed some hypothesis testing procedures. I took that to a climate model meeting, and they yelled and screamed that that's not the internal variability, that there's a whole notion of internal variability specific to that field, and they didn't want to think about this one. And if it does, if this can be convincing to climate modeling people, then maybe there's a whole enterprise in formulating hypothesis tests to assess whether two climate model runs are similar or whether a climate model run produces a data set that is similar to an observed one. And I'm going to stop there. It's probably lunchtime by now. There's some references and there's some contact information. So thank you. And we'll get, yeah. And I, yeah.
Hi. Hi, thanks, Amy.
Mhm.
I wanted to ask, and this relates to your question on natural variability. I want to ask, like, what happens when you have like massive data imbalances or outliers, your data? So like, 99% of the clouds you see are, not saying this as a fact, but if your data is like mostly liquid water clouds, what happens when you're trying to simulate those ice clouds, which are just as important? What happens when your data has a hurricane?
Right. So that was a reason for using the actual data as the source, as the parent, right? I mean, if it's in, you're right. I mean, the algorithm that gave rise to the parent data set, which is actually the retrieved data set, might have all kinds of problems in it. It's true. But, and this did come up in the model discrepancy part of the work, which is you kind of have to make the assumption that your retrieved data is at least good enough that you can regard the truth as a realization from the same process that gave you the retrieval. It's not the same realization, but it's a different realization. So and my argument for that, I thought I was being very sly, was to say that if the people that produce these data sets can't say that, then they have no business putting this out to the community and saying this is a representation of reality. So like with many things, I mean, we live with the sample we have. It is possible that if you wanted to explore the impact of something like that, you could do it as kind of a simulation experiment where you force those artifacts in and see what happens and quantify the properties of the truth given the retrieved, which in that case, if there's, should show bias. If that were true, because presumably you're asking because the ice clouds and the water clouds have different effects on the radiance. Yeah.
Thank you.
We have a couple of questions from online. First, how do you handle the backscattering component? And from the same guest, would you please let me know how you have included the aerosol data to the radiance distribution?
Okay, those are all, I think they're both radiative transfer questions. That has to do with the forward model F and the retrieval. And that answer would have to come from my collaborator, Nicholas Bond, who ran those algorithms.
I think we have time for one more question in the room or online.
Thanks, really interesting talk. I'm wondering if you could give a very quick summary of your model discrepancy construction talk.
Oh yeah, I figured people would want to hear about that. I did. So let me see what I can do here.
There's a 4 o'clock slot.
Yeah, I do. And if you're the person who was online in the meeting I had with Greg and Marcus and Larry Tutuba, is that you?
Oh.
No, okay, never mind. Okay, so here's the discrepancy stuff, right? Which is what we're interested in is this term, this delta X. This is notation that is supposed to suggest that at the true X, the true state, the difference between what you get when you apply the forward function and the forward model, whatever that is. And if you do a little, one thing we routinely have access to in remote sensing data processing is something that's called the spectral residual, which is the difference between the observed radiance Y and the so-called model radiance Y hat, which is what you get when you stuff your retrieved estimate back into your forward model. And we want to leverage that. And so if you do a little bit of algebra, you see that the spectral residual with the error term can be decomposed into two pieces. One is the piece we want, and the other is the other piece is the impact of using the wrong X if you apply the forward model to those two pieces. Now, a little more algebra, you end up with this, which is that if you take the observed radiance is y minus epsilon here, the sign changed just because stuff was moving around. And this piece here, and this is the problematic piece because I don't really know what X is, but if I'm willing to make this assumption that X is a draw from the same distribution that gave rise to those X stars, then I can do this with that approximation. And it does seem in a toy example, it certainly produced something not exactly right, but interesting and useful. And in this example, I suspect that some of those artifacts were due to the way the model discrepancy was done. So it's the lowest, least intrusive assumption one could make and still believe that there's any skill whatsoever to your retrieval. So I'm happy to talk about that more later if people want to.
All right. I think that's all the time we have. Amy, thank you so much for your
Welcome.
time and your presentation.
Thank you.